Okay, so this is going to be a short session for physical science for the beginning of the section on light, 5.1, the nature of light. Now this is a short section anyway, and we do have a review video that goes over parts of it, and there's not practice exercises to go over for this one because there's no math. So instead today I'm just going to talk about one topic that's in here that we didn't get to go over too thoroughly in the other review video, and that is the photoelectric effect. So real quick, why this matters to understand that, we've got to go through the history of understanding light. So scientists in the 1700s thought that light was made of particles. We know that all things are made up of atoms. It turns out light is not. Light is pure energy, but they thought it was made of some kind of particle. And so they thought this up through the 1700s. And reasons for that was that it only traveled in a straight line, and waves could do curvy things, and it traveled in a vacuum and other waves cannot. But in the early 1800s, scientists did some work to show that light was a wave and it had to be a wave. And reasons for that was that light experienced interference and diffraction. Those are two properties of waves that don't happen with solid particles. They only happen with waves. And they figured out that, okay, one of the previous arguments was it can't travel through a vacuum, but now we understand how it travels through a vacuum. And then our third main thing, and this is what we're talking about today, was in 1905, Albert Einstein showed that light has properties of a wave and of a particle. So before that, it was it a particle? Was it a wave? Is it particle or wave, particle or wave? And his answer is both. And so we're going to look at how the photoelectric effect actually shows that. So what happens is that sometimes a light wave can hit a piece of metal and eject an electron. So the ray of light hits the metal, and again, we know that light is energy. Light has lots of energy. It gives energy to that metal. The energy goes into electron. The electron gets thrown out off of the metal. It gets ejected. But what's important is this only happens at some frequencies. So some frequencies of light will make this happen and others won't. Now, if light was purely a wave, the frequency wouldn't matter. If it got hit with a low frequency and there wasn't enough energy to make that electron eject, then we could just pile on more light waves. If we make the wave more intense and just add more and more and more energy, the electron will finally get enough energy to pop off of that metal. So that's what would happen if light was purely a wave, but that doesn't happen. We can't make this happen with low frequencies of light. It won't happen no matter how much we increase the intensity, the electron won't move. At low frequencies, and that's what this slide is, at low frequencies, we apply some light, nothing happens. We keep applying more light and nothing happens. No matter how intense we make the light, if we don't change that frequency to get higher, no electron moves. And conversely, if we're using a high frequency, and a higher frequency means the rays of light are going to have more energy, at a high frequency, even a really weak beam of light will make the electron eject. So it's really weird that only the frequency matters. We can't just pile on more energy by having more light there and make it make a difference. And we could have barely any energy, seemingly, if we use a high frequency, but it still ejects that electron. So this proves through the math that they figured out, this shows that light cannot just be purely a wave, because we said that's not what would happen if light was a wave. If it was just a wave, you could just add more light waves, a higher intensity, and get enough energy for that electron to go. So what this has to mean is that light is not just a continuous wave. Light comes in separate chunks. And the word for that is quantized. Okay, so there are certain amounts of energy that light can have, and it can't really be in between those amounts. The smallest amount of light energy is 1 photon, and that's kind of what we think of as the particle for light. So this experiment shows us that light can't just be a wave, so it has to have particles. And we call those particles photons. And again, just to reiterate, the effect of many photons can't build up. an individual photon has to have enough energy to affect the electron. So the scientists before this showed that light has to be a wave because it does that diffraction thing and it does interference. And this experiment shows that light has to be a particle because of the way that it affects the electrons. So what they came up with is that light is both. It has a frequency and it comes in units called photons. It is both a wave and a particle. And the official term for this is wave-particle duality. That means that light is seen sometimes as a particle and sometimes as a wave. It is both at once. And this is super important because it was an early discovery in the field of quantum mechanics. So Einstein's work with light and figuring out that it does act as a particle while also acting as a wave kind of just opened the door for this whole new branch of physics, and it changed the way that we understand everything about the universe. So it was one of the first steps in the field of quantum mechanics. And Einstein's shown here with some other scientists of the time, some of which also worked in quantum mechanics. So I hope that helped explain what the photoelectric effect is and why it matters. And that's the end of this section. If you have any questions on it, definitely don't hesitate to contact your instructor.